Hybrid electric vehicles. In this unit, the topics history, types of hybrid electric vehicles, and design of hybrid electric vehicles. What is a hybrid electric vehicle? A hybrid electric vehicle is a type of vehicle that uses a combination of an internal combustion engine and an electric propulsion system. The electric powertrain may enhance the fuel efficiency, increase performance, or independently propel the vehicle on pure electric power depending on the type of hybrid. In simple words, an hybrid electric vehicle is a vehicle that comprises a conventional fuel engine and an electric powertrain, wherein the electric motor assists the engine to extract more performance and better fuel economy depending on the type of the system, and we will elaborate the kinds of hybrid electrical vehicles in the remaining slides. How does an electric vehicle works? Unlike an electric vehicle, the working mechanism of an hybrid electric vehicle is relatively simple to understand. The points shown in this particular slide. Powering a hybrid electrical vehicle is an I.C.E engine and an electric motor. The electric motor utilizes the electrical energy stored in the battery pack. The battery pack gets charged through regenerative braking or through a generator that is run by the internal combustion engine. An hybrid electric vehicle does not need to be plugged into a power source to charge the battery. The electric motor and I.C. engine work in conjunction to propel the vehicle. The additional power from the electric motor assists the engine and it enhances the performance and improves the fuel economy. The battery pack can also power other electrical components such as lights. The electric powertrain also saves fuel through the engine start or stop technology, wherein the engine automatically shuts off when idle and starts automatically when the drive presses the throttle pedal. Components of a hybrid electric vehicle: battery, DC to DC converter, electric generator, electric traction motor, exhaust system, fuel filler, fuel tank, internal combustion engine, power electronic controller, thermal system, traction battery pack, transmission. Internal combustion engine. The primary power source of an hybrid electrical vehicle is a conventional engine. Hence, it is the main component responsible for propelling the vehicle. An hybrid electric vehicle cannot run alone on an electric powertrain without an engine. Electric motor. The secondary power source of an hybrid electric vehicle is the electric motor. It assists the engine during initial acceleration to improve the performance and fuel economy. It runs on electrical energy stored in the battery pack. It can also change the battery when the vehicle is braking or coasting through the regenerative braking system. Battery pack. A battery pack powers the electric motor. Basically, it acts as a fuel tank for the battery, wherein it stores the electrical energy through regenerative braking and the generator driven by the I.C. engine. The battery pack can also power auxiliary electrical components such as lights. Generator. It is an essential component found in the series hybrid vehicle. We will touch upon what series hybrid is in upcoming slides. A generator draws the power from the I.C. engine to power the electric motor and the charge the battery pack. In simple words, a generator converts the mechanical energy into electrical energy. Next component, transmission. Typically, hybrid electrical vehicle use conventional transmissions similar to petrol or diesel vehicles. It transmits the power produced by the IC engine to the drive shaft. The basic working principle of transmission remains the same even in an hybrid electrical vehicles. It is one of the crucial components required to propel the vehicle. Fuel tank. Similar to a conventional vehicle, hybrid electrical vehicles also have a fuel tank to store the conventional fuel. With electric powertrain involved in a hybrid vehicle, the fuel consumption will be comparatively less than a vehicle purely relying on an IC engine. Advantages of hybrid electric vehicles. Switching to a hybrid vehicle has many advantages, a few of which we have highlighted in this slide. Environmental friendly, economical, less fossil fuel depend, regenerative braking system, light bullet, higher resale value. And coming to the disadvantages of hybrid electrical vehicles, less power, expensive to purchase, poor handling, high maintenance cost, high voltage batteries. So these are the disadvantages of hybrid electrical vehicles. Types of hybrid electric vehicles. There are three types of hybrid electric vehicles: series hybrid, parallel hybrid, series parallel hybrid. Coming to the series hybrid system, in case of the series hybrid system, the mechanical output is first converted into electricity using a generator. Conceptually, it is an ICE assist the electrical vehicle. The advantages of series hybrid driven systems are mechanical decoupling between the IC and the driven wheels allows the IC engine operating at its very narrow optimal region. Nearly ideal torque speed characteristics of the electric motor make multi gear transmission unnecessary. And however, a series hybrid drivetrain has the disadvantages. The energy is converted twice, and this reduces the overall efficiency. Two electric machines are needed, and a big traction motor is required because it is very only torque source of the driven wheel. In this series hybrid system, the IC engine powers the electric generator which drives the electric motor and charges the battery. In this setup, the engine does not directly power the wheels. Series hybrid is also called a range extender since the engine powers the electric motor and the battery pack. And second type, parallel hybrid. In this system, both the engine and electric motor work parallel to propel the vehicle. The engine and the electric motor deliver optimum power for the efficiency functioning of the vehicle. The battery pack gets charged through regenerative braking. If you wonder what regenerative braking is, here a brief explanation. Regenerative braking is a process of utilizing the kinetic energy produced while slowing the vehicle down to the charge the battery pack. And coming to in this process, so the parallel hybrid system allows both IC and electrical motors. The advantages of parallel hybrid driven train are both engine and electric motor directly supply torques to the driven wheels and no energy form conversion occurs, hence energy loss is less. Compactness due to no need of the generator and smaller traction motor. The drawbacks of parallel hybrid driven trains are mechanical coupling between the engines and the driven wheels, Thus, the engine operating points cannot be fixed in a narrow speed region. The mechanical configuration and control strategy are complex compared to the series hybrid drivetrain. Due to its compact characteristics, small vehicles use parallel configuration. Most passenger vehicles employ this configuration. Coming to the third type, series parallel hybrid. A series parallel is a flexible system wherein the IC engine and electric motor can work in conjunction or independently. The power deliver or power distribution helps the vehicle achieve maximum efficiency in terms of power output or fuel efficiency. And in this particular section, series parallel system, in this parallel series parallel hybrid, the configuration incorporates the features of both series and parallel hybrid electrical vehicles. However, this configuration needs an additional electric machine and a planetary gear unit, making the control complex. The complex hybrid system involves a complex configuration which cannot be classified into the three kinds. The complex hybrid is similar to the series parallel hybrid since the generator and electrical motor is both electrical machines. However, the key difference is due to the bidirectional power flow of the electrical motor in complex hybrid and unidirectional power flow of the generator in the series parallel hybrid. The major disadvantages of complex hybrid is higher complexity. Due to the various hybrid electrical vehicle configuration, different power control strategies are necessary to regulate the power flow to or from different components. All the control strategies aim to satisfy the goals. The first goal is the maximum fuel efficiency, second one minimum emissions, and third one minimum system cost, fourth one good driving performance. The design of power control strategy for hybrid electrical vehicles involves different considerations such as optimal IC operating point. The optimal operating point on the torque speed plane of the ICE can be based on maximization of the fuel economy, the minimization of the emissions, or a compromise between the fuel economy and emissions. Coming to the optimal ICE operating line, in case of ICE needs to deliver different power demands, the corresponding optimal operating points constitute an optimal operating line. The power flow control in series hybrids system, there are four operating modes on the power flow. Schematic of series system and schematic of parallel system shown in this particular slides, and gasoline fuel cell and internal combustion engine, generator, battery, electric motor, transmission system. These are the components in the schematic of the series system. And coming to the schematic of the parallel system, and here is this, and gasoline fuel cells, engine controller, internal combustion engine, transmission control device, electric motor, motor generator or control, and battery. And these are the components in this particular schematic parallel system. Hybrid electrical vehicle drive systems are very complex and vary greatly from vehicle to vehicle. The batteries are generally balanced. They are either centered or distributed between the front and rear of the vehicle because they are heavy and take up a lot of volume. All other components are arranged for maximum efficiency and continue. The number of electrical motor varies and does the number non-electric torque sources. The presence of the two power sources makes a switching mechanism necessary. Most hybrid electrical vehicle systems also allow both IC engines and electric motors to work simultaneously. and the figure only shows the one possible drive system, as in the choice of the battery type, non-electric torque source, and most everything is related to the hybrid electrical vehicle systems. Coming to the dominant of the physics here, the flow of power through the hybrid system and the efficiencies and mechanics of the components and connections therein comprise the most important physics in the hybrid electrical systems. For the components used, the objective of the hybrid electrical vehicle designer is to connect the control each part so that maximum efficiency is achieved. An internal combustion engine runs most efficiently at higher speeds, so it is used alone in the highway driving. It is very inefficient in stop and go traffic. However, an electric motor would soon deplete its battery on a long highway drive, but can drive the vehicle efficiently through city traffic with no emissions to release into the city atmosphere. Of course, there are driving modes in between these when both ICE and electric motor work in a tandem, as when the vehicle is accelerating. The power flow through the drive mechanism depends on the arrangements of the system and several clutches which engage and de-engage components from the assembly. In this diagram, the solenoid clutch 1 controls the connection between the ICE and generator. Solenoid clutch 2 controls the connection between the ICE and transmission. Overrunning clutch 3 controls the connection between the ICE and system. Overrunning clutch 4 and 5 control the connections between the electric motor and the system. And this diagram shows the power from ICE only. Red color indicates the solenoid clutch. The power flow from the internal combustion engine through the secondary drive shaft to the transmission. It is then flows from the transmission to the primary drive shaft and then to the wheels. Overrunning clutches 3 and 5 are engaged and all other are disengaged here. The next slide here is power from the electric motors only. Red color indicates the solenoid clutch. So in this, the power flows from both the electric motors through the transmission and to the drive shaft and the tires. Overrunning clutches 4 and 5 engaged and all other are de-energized. Coming to the next diagram, and this diagram shows the power from ICE and electric motors. Red color indicates the solenoid clutch. So in this diagram, power flows from the internal combustion engine through the secondary drive shaft, through the transmission, and then to the primary drive shaft, and then to the tires. Power also flows from both electric motors to the transmission and then to the primary drive shaft and the tires. Overrunning clutches 3, 4 and 5 are engaged and solenoid clutch 2 is engaged and all other are de-engaged here. Coming to the next slide, that is charging battery with wheel motion. In this diagram also, red color indicates the solenoid clutch. So in this diagram, power flows from the wheels to the primary drive shaft, then through the transmission, through the secondary drive shaft and to the generator and finally to the batteries. This occurs during the regenerative braking. Solenoid clutches 1 and 2 are engaged All other clutches are de-energized, de-engaged here. Coming to the next slide, I.C.E provides power and charges battery. And in this also red color indicates the solenoid clutch. So here the power flows from the internal combustion engine through drive shaft to the transmission and then to drive the shaft 1 and the tires. Power also flows from I.C.E through the drive shaft 2 and the generator. Overrunning clutches 3 and solenoid clutch 1 are engaged and all other are disengaged here. Coming to the next slide, here is electric motors provide power. I.C.E charges the battery. In this also red color indicates the solenoid clutch. The power flows from the internal combustion engine through the secondary drive shaft to the transmission, then through the primary drive shaft and the tires. The I.C.E also provides the power to the generator through solenoid clutch 1 and then to the battery also. The electric motors provides power to the primary drive shaft through the transmission. All clutches are engaged here. Mainly hybrid electrical vehicles and other non-hybrid electrical vehicles also use regenerative braking. This system takes some of the energy normally dissipated by friction when the car is braking and convert it back to the usable energy. Now, in this particular scenario, the wheel shaft rotating at speed W with torque T generates the power P all the functions of the time. Taking power from the wheels would slow the vehicle down, which is normally undesirable except in braking. When the brakes are applied, the shaft of the generator is connected to the wheel shaft, so it can be rotated by the power of the wheels. The generator then converts this mechanical or rotational power to the electrical power. The hybrid electrical vehicles also charges the battery with the I.C.E through the same process. When the vehicle is in motion, a controller monitors the state of the battery and the speed of the I.C.E. When battery charge is low and I.C.E speed is high, it connects the drive shaft of the engine to the generator, drawing power from the I.C.E to charge the battery. Because this controller is in place, the vehicle will not lose power when accelerating, hill climbing, or otherwise in need of the full power. And coming to the limiting physics here. The performance of the hybrid electric vehicles is limited by its efficiency and its capacity to carry its own fuel. Battery capacity and fuel energy density are both limits on the amount of power vehicle can sustain. And here on this particular table, the three major types of the battery are lead acid, nickel cadmium, and nickel metal hydride. Battery specific energy, specific power, cost and life are the most important factors in the choosing of the battery. And coming to the here is lead acid battery, the specific energy 35, specific power 200, appropriate cost is the 125 and approximate lifespan is the 450. And coming to the nickel cadmium, specific energy 40, specific power is 175 and approximate cost is the 600 and approximate lifespan is the 1250. And third one is the nickel metal hydride, specific energy 70, specific power 150, approximate cost is 540 and approximate life is the 1500. The units for the specific energy or power is measured per unit of the mass. This is important because any battery assembly will provide enough energy provided there are enough batteries, but the hybrid electrical vehicles has only limited volume and carrying capacity. So it needs to use battery with high energy power density.